Now we'll look at several examples of solving quadratic equations graphically. We want to use the graph of y equals x squared plus x minus 6 provided here in red to solve the equation x squared plus x minus 6 equals 0. If we compare these two equations, notice that y has been replaced with 0. When we're given the equation of a function, replacing y with 0 and solving for x is the process for finding the x-intercepts. So we can solve this equation here graphically by finding the x-intercepts of our function, which occur here and here where the function crosses the x-axis. Notice the coordinates of this x-intercept would be 2, 0, and the coordinates of this x-intercept would be -3, 0. Notice for this x-intercept, this is telling us that when x is equal to 2, y is equal to 0, so x equals 2 would be a solution to this equation. Or when x is equal to -3, y is also equal to 0, and therefore x equals -3 would be a solution to our equation. So in general, when we have an equation equal to 0, and we replace 0 with y and graph the function, the solutions will be the x-intercepts. Notice for this quadratic equation, we have two real rational solutions. Let's take a look at another example. Here we want to use the graph of y equals -x squared plus 4 to solve the equation -x squared plus 4 equals 0. So because this equation is equal to 0, the solutions will be the x-intercepts of y equals -x squared plus 4. So again, we have two solutions, one here and one here. The coordinates of this x-intercept would be 2, 0. The coordinates of this x-intercept would be -2, 0. Again, these are the x values where y is equal to 0, which would be solutions to this equation. So our two solutions are x equals 2 or x equals -2. And again, we have two real rational solutions. In this example, we want to use the graph of y equals x squared minus 2x plus 1 to solve x squared minus 2x plus 1 equals 0. And notice this graph is a little bit different. It doesn't pass through the x-axis. The graph only touches the x-axis at x equals 1. This is what happens when the solution has multiplicity 2, or we can say is a double 0. So the x-intercept here is the point 1, 0. So our solution is x equals 1. But again, because it touches the x-axis and doesn't pass through it, we can say the solution has multiplicity of 2. We can also say it's a double 0 or a double root. So in this case, we only have one real rational solution. Another way to see why we say this has multiplicity of 2, if we actually try to solve this by factoring, it would factor into two binomial factors. We want the factors of positive 1 that add the -2. So we'd have x minus 1 times x minus 1. Notice how the factor of x minus 1 occurs twice, which is also another reason why we can say x equals 1 has multiplicity of 2. We have two factors of x minus 1. But this is how it looks graphically. In our last example, we want to use the graph of y equals x squared plus 1 to solve x squared plus 1 equals 0. But in this example, notice how we're looking for the x-intercepts, but this graph does not have any x-intercepts. So that means there are no real solutions to this equation. But if we tried to solve this algebraically, we could isolate the x squared by subtracting 1 on both sides. This would give us x squared equals -1. If we take the square root of both sides of the equation, remember we need a plus or minus sign here, we would have x equals plus or minus, well, the square root of -1 is equal to I. So now to be more specific about the types of solutions we have here, we could say that this equation has two imaginary solutions. And that's the reason why there are no x-intercepts. The x-axis is a real number line. Therefore, if a quadratic equation does not have any real solutions, the corresponding quadratic function will not have any x-intercepts. Okay, I hope you found this helpful.